when we think about curves, we want to come up with an analytical way to understand how much the curve is curving at any given moment. Since for what we call a curve is really just a defined way of moving through space. If we look at a curve, this curve described by C, if we look at the point P, if we notice if the red and blue are tangent vectors at each of these individual points, we see that the tangent vector through P changes a decent amount. It moves a lot going from P to Q. But if we move further along the curve from R to S, they have basically the same tangent vector. So the change in tangent vector is very small there, whereas it's very large at P. So it's large at P, it's very small at R. And so we can describe the curvature as a function of how that tangent vector is sweeping through. If the tangent vector changes quickly, we know that we have large curvature. If it changes slowly, we have no curvature because you're just continuing along in the same path. The analytical way to do that, this curvature, kappa, so you can call it K, I might even call it K, but usually it's denoted with the Greek kappa. Some smooth curve is really the measure of the change of that tangent vector with respect to S. So it's not how much the tangent vector is changing over time per se, it's how quickly is it changing as it moves a certain distance along the curve. The reason why we don't want to do it with respect to time is that you could define the curve in such a way that it moves very slowly with respect to time. But the curve should still be moving, so you want to say, all right, if I cover this much distance, and over that distance, the tangent vector went like that, that's a lot of movement of that distance over time. So that tells us there's a large curvature. So what we do is we take the change in the tangent with respect to the arc length parameter. Or we could think of this magnitude of t prime at s. But finding that's difficult because, well, first we need to find that arc length parameter. Well, that's an integration problem. Then we have to solve for t in terms of s because we're going to eventually be plugging in s here, not t. Then to find t, we have to find r prime. We have to find the magnitude of r prime. We get t from dividing these two. Then we have to find the derivative of t at t. Then we have to take this piece, plug it in, t prime of s, and then we still have to take another magnitude. So there's a lot of steps there, and some of them are fairly non-trivial, specifically that one. Now, if we use this formulation, we're used to finding t, so we can use r prime and find the magnitude of r prime, and that can be a little tricky. So finding t is simply taking this divided by that. Then we have to find its derivative, which might be tricky depending on how nasty that is. And then we have to find its magnitude, which can also be kind of gross if that one's gross. And then we have to take that magnitude and divide by this one's magnitude. So it's still a lot of work. So there's a third formulation, and this is the one I probably prefer. Finding r prime and r double prime isn't so bad. Crossing them can be fairly nasty, but that's more so nasty from writing a lot of things on a page as opposed to having to keep up with a lot of really tricky algebra and square roots and things like that. Then we need to be able to find the magnitude of r prime so that we can cube it later. And then once we've found this vector, which usually kind of expands and then contracts once you've done all the addition and subtraction, finding its magnitude is no different than finding the magnitude of any other vector. And then we put those together. So for my money, I tend to prefer this one. However, each of these has their merits, especially if you already have information about what the arc length parameter is and such. And this one, maybe if you have information about the tangent vector already, or there's some sort of, you can use some sort of cleverness. The idea is that they're all available to you, but I would usually start with this one unless you have a good reason to use the other two.